So now we're going to look at how do we draw the Lewis structure for simple molecules, and I should add also for polyatomic ions. So we talked about Lewis symbols for elements, and it's a very simple representation of atoms of an element where we simply write down the symbol for the element itself, and then we use dots to represent the valence electrons. So the Lewis structure for a molecule is basically showing you how the atoms are put together using the same symbolism for electrons, using dots, and also using some other representations for the formation of covalent bonds between atoms, all right? So we're going to get into how we can actually determine the Lewis structures for those sort of structures. Now, in most cases, not in all, because there are some exceptions, but in most cases, what you'll find is that each atom will end up with a noble gas configuration, or in other words, will end up with 8 electrons on its outer shell in these structures. But there are some exceptions, and we're going to get into those exceptions later on. Also, hydrogen, of course, cannot have 8 electrons, so therefore hydrogen will have 2 electrons on its outer shell because it obeys the duet rule, all right? And the shared electrons can be counted for each atom that shares them, so that you'll notice that in most cases, again, let me just emphasize most cases, each atom will have a noble gas configuration. Okay, so let's talk about some symbolism and terminology with respect to Lewis structures. So when you look at the Lewis structure of a molecule such as chlorine, which is what you see here, of course, we have individual Lewis symbols for the chlorine atoms, and then of course when they share the single electron that they both have, which is unpaired, you end up with the molecular structure. So therefore this is the Lewis symbol or structure for the chlorine molecule. Now, if you look at this, of course, you'll see that each chlorine atom will end up with 2, 4, 6, 8 electrons, all right? Now, at this juncture, it's important that we make a distinction between what is known as the bonding pairs of electrons and the lone pairs, because that will become important, especially later on when you're learning about molecular shapes. But before we do that, let me just say that, well, let me just go straight into the bonding pairs. So the bonding pairs of electrons, of course, are those electrons that are shared between the two atoms. So in this case, in the case of chlorine, we have a bonding pair that is being shared between the two chlorine atoms. Now, a common practice, instead of using dots to represent the bonding pair, we can use a dash or a line, right? So it would look something like this right here, right? So this line here would represent the same thing as the two electrons being shared between the two chlorine atoms, all right? Now, all other electrons which are not being shared between the two atoms are called non-bonding pairs or lone pairs, right? So going back to the chlorine example, each chlorine atom will have 1, 2, 3 lone pairs of electrons or non-bonding pairs of electrons, all right? So it's very important that you are able to distinguish between the two and understand the representation of the Lewis symbol for a particular molecule, in this case chlorine. And let me just say, there's also one other representation that you would see in some textbooks. It would look something like this, using it to apply to the chlorine molecule. I'm just going to write it right in the middle right here. It's going to be Cl, Cl, and you can have lines like this, which represents the lone pairs, right? So this, let me just use an arrow here. So the bonding pair, of course, would be the line that is between the two atoms, but the lone pairs would be the lines that are not between the two atoms, all right? So that's another representation that I've seen in some textbooks, which, personally speaking, I prefer to use, but of course, you know, there are other alternatives. You can use this representation, or this representation, or my personal preference, this representation, all right? So, you know, I won't penalize if you use any of the others. As far as I'm concerned, they're all just as correct, all right? Okay, so just to give you some examples of molecules and their Lewis symbols, we're looking here at particular elements in period 2, carbon, nitrogen, oxygen, and fluorine, and the compounds they form when they combine with hydrogen. So in the case of carbon, it combines with 4 hydrogen atoms to form methane. So this would be the Lewis structure for methane. In the case of ammonia, you'll notice that you have the nitrogen bonded to 3 hydrogens, but it also has a lone pair here. And by the way, going back to the methane example, this carbon here has 4 bonding pairs and no lone pairs. And each hydrogen has 1 bonding pair and no lone pairs. And that is true for hydrogen whenever they exist in a molecule. Hydrogen will never have any lone pairs of electrons. In fact, hydrogen will only have 1 bonding pair if it's combined with another element. So going back to the ammonia, the nitrogen here has 3 bonding pairs and 1 lone pair. In the case of water, the oxygen is bonded to 2 hydrogens, so therefore it has 2 bonding pairs and 2 lone pairs. And then in the case of hydrogen fluoride, the fluorine is bonded to the hydrogen here, so there's 1 bonding pair, and the fluorine has 3 lone pairs. All right. So that's basically the Lewis symbols or the Lewis structures for these molecules. All right. So some important information down here in this green box. It says here that no, the 2-dimensional Lewis structures do not necessarily show the correct shapes of the 3-dimensional molecules. And that's not their purpose, right? The purpose of Lewis symbols or Lewis structures is not to show the 3-dimensional shapes of molecules. Now, the key thing you need to know is that you're going to need the Lewis structures in order to make that prediction. But the Lewis structures themselves do not show the 3-dimensional shapes of the molecules. It just basically shows you how the atoms are connected to each other and shows you all the bonding pairs and lone pairs of electrons that are involved. All right. So as stated here, the Lewis structure for water could be drawn like this, or it could be drawn in a straight line like this. It doesn't matter. We're not concerned when it comes to Lewis structures. We're not concerned with the 3-dimensional shapes of the molecules, right? But as I said before, later on, we're going to learn about predicting the shapes of molecules based on the Lewis structures. All right. Okay. Another thing that we need to talk about when it comes to Lewis structures is that you can have the formation of what is known as multiple bonds. All right. So a covalent bond, right, is basically the result of the sharing of a pair of electrons, right? So basically a pair of electrons will constitute, that is shared between 2 atoms, it will constitute a single bond. Now you can have the formation of multiple bonds, as you can see here in the case of carbon dioxide, right? So in the case of carbon dioxide, this carbon here, you'll notice you have 2 lines here between this carbon and this oxygen. Each line represents a pair of electrons. So basically, in the case of carbon dioxide, you have 4 electrons being shared between the carbon and this oxygen, and the same is true on this side, all right? So we call this a double bond, right? Because you have 2 pairs of electrons being shared between the 2 atoms, carbon and oxygen. You can also have a triple bond, such as in the case of nitrogen, all right? And you'll notice that in all of these cases, the atoms will have 8 electrons on their outer shell, or the octet being satisfied for each atom. So for this carbon here, it has 2, 4, 6, 8 electrons on its outer shell. And the same is true for each nitrogen. Each nitrogen will have 2, 4, 6. Those are the bonding pairs. And then we have a lone pair here. So that's a total of 8 electrons for this nitrogen. And the same is true for this nitrogen. All right. You can also have up to the quadruple bond, but we won't get into that. That's a bit beyond our scope. For our purposes, the bonds that we'll be meeting in terms of multiplicity would be triple and double bond, and then there's a single bond, and that's it, right? So that's basically what we'll be learning about in this course. Okay, so I want to point out this particular example of oxygen, right? This is a Lewis structure of oxygen, which is the structure that is commonly drawn, right? And you'll notice that in this structure here, all the lone pairs are, well, you have 2 lone pairs for each oxygen atom. So therefore, this seems to indicate that all the electrons are paired in the case of oxygen, if you were to go by what you see here as a Lewis structure representing the oxygen molecule, all right? Now, if you remember, in the previous chapter, we talked about paramagnetism, right? Paramagnetism is basically displayed by molecules which has unpaired electrons, right? And it turns out that there's experimental evidence for oxygen to be paramagnetic, right? Because what will happen if you pour liquid oxygen between the poles of a magnet is that the liquid oxygen will be held between the 2 poles, right? And if you remember, paramagnetism is the attraction that a substance will have for a magnetic field, and that's exactly what's happening here. The oxygen is attracted to the magnetic field that is produced by the two poles of the magnet. So therefore, that is experimental evidence that the oxygen molecule is paramagnetic. In other words, the oxygen molecule has unpaired electrons, and therefore the Lewis structure here that is drawn typically for oxygen is not an accurate representation of how the electrons are distributed. The electrons, especially the lone pairs on the oxygen, will be unpaired, all right? And therefore, this is not a true representation of the oxygen molecule. So more than likely, if you were to draw the Lewis structure representing, based on this experimental evidence, it would look something like this. Let me see if I can put it, hold on 1 minute. Let me see if I can put it up here. So the Lewis symbol will look something like this. O, double bond, O, and then you're going to have that would be a more accurate representation, because now we see that these oxygens here, these electrons here are unpaired, all right? Okay, so that's an example of the importance of experimental evidence, right? You might have a theoretical explanation for one thing, and then the evidence turns out that, or proves that, whatever the theory that you had before would not be accurate because it doesn't fit with the data or the evidence that the experiment provides. So, as stated here, the Lewis structures are a useful tool, but they do not represent always the molecules correctly, even when the Lewis structure is plausible. So, in most cases, when it comes to drawing Lewis structures, we would stick to using this, for example, for oxygen, but we have to keep in mind that this is not always an accurate representation of the true structure of oxygen. Okay, so we're going to stop here for this video. And then what we're going to do in the next video is learn how to draw the Lewis structures for different molecules and polyatomic ions. All right? Okay, until next time.